Okay, let's go ahead and start a little bit in advance. So Mina generously gave us a little bit of time so that we can finish, because I really want to make sure you have the big picture before we start doing the hands-on parts. So let's just review a little bit where we are, right? So we take a data set. We start by finding the values that we don't trust. And we do this by establishing this cutoff, which is somewhat empirical, but it seems to work okay. And essentially we say that all the values below that will be treated as missing for reasons of low abundance, unless we are working with some tools which tell us that some type of missing values are due to other reasons, in which case we will not. We will leave them alone and will not do anything to them. Okay, and so the next step is to focus on the technology part, right? So we ignore for the moment the fact that different runs come from different conditions, different subjects, and all of that. So we'll just say, let's look at this like literally as a two-way table where the rows are features, the columns are runs, and we have some missing values. And so what we want to do is to look essentially on one hand at the fact that different features have different ionization efficiency. So they have higher intensity than others on the log scale. And then different runs, some runs have more of the protein than other, just because for whatever reason the protein was more abundant. And so when we have so what each log intensity here will have a contribution from the feature, and it will be characterized by the representative signal of the feature, and each run will be characterized by the representative signal of the run. And so when we try to estimate what is the value, representative value of the feature, and what is the representative value of the run, so the procedure, so if we didn't have missing values, we would essentially do some averages, but in presence of missing values, we have to work with censored values, and the procedure is called maximum likelihood, and this procedure specifies that the missing values, so below this vertical line, will be below the limit of detection, and it allows us to get a better characterization of the level of individual feature, better characterization of the individual run, and then we can predict what the values of these missing values would have been if we really have each value impacted by the feature and by the run. So as I say, I'm hand waving a little bit that it would take a little bit more complications to explain exactly what it does. But essentially, it is better than assuming that it is missing, because, for example, if you assume that it is just missing, then it will be only influenced by the high intensity features, and low intensity features will not be part of this summarization. And we say that these values are missing and are low, then it reduces the overall summarization. Does it make sense? Or you are lost? Somebody wants me to repeat it in a different way? I need to have those yellow-green stickers. That would be good. So, really, okay? So, well, maybe let me just still make just one picture, just in case I can find. So, essentially, if I make a plot like that, just to present it different, let's say this is run, this is log intensity. So we have run 1, 2, and 3. Let's say here would be our value, right? So this is feature 1, feature 2, and feature 3, right? And so now if these two values were actually censored, so they could not be quantified because the analyte was below the limit of detection, if we only summarize this run by this feature, then we overestimate the abundance of the protein in this run. But if we say that these two values should be low, then it allows us to have some summary which will be lower than the feature that we actually observe. So that's the idea. Yes?
Okay, so for this model, when you say it's below the limit of detection, is it completely undetected, or is it just below the limit of quantification, or it doesn't matter?
So, oh well, so there are two ways to answer it, right? So if you work with targeted assays, you actually characterize the assay in terms of limit of detection, limit of quantification, limit of blank, and all of that, right? And so this is one way to proceed. So if you work with assays which have really good characterization, you can actually select this threshold based on what you know about the assay. The problem is that our data often are not like that, right? We work with discovery experiments or DIA, which do not have really strict characterization for each protein. Then essentially we're saying it's below the value which makes sense to us. And this may or may not represent limit of detection or limit of detection, but we may not just have enough data to even know what these numbers are. So we just say it's below what is visible to us for whatever reason. Yeah, but really good question. Okay, so that's what we do. And so once we have these values predicted, so we still may be affected by outliers. So let's say this particular peak, for whatever reason, was misquantified and it went somewhere here, right? And so now we have a pattern which is very different from the rest of the patterns of these features. So if we now try to summarize this somehow, let's say with the average, it will be very much affected by this outlying peak. A robust summarization instead will say, okay, this is just one number, the majority of numbers are here, and it will lower the summary, so it will also be more resistant to individual outliers. So the first step with imputing missing values focuses primarily on missing values, but it's affected by outliers. The second step will now eliminate some of the artifacts of outlying values. And so after this summarization, we have one number per protein per run. And this is pretty much now in the framework of what we did last week, right? So, yes?
That's a good question. So the example you had here, it's within a protein.
Sorry?
It's within a protein. It's not trying to draw conclusions about the protein which you don't see.
So this, everything, let's say it's a protein that has 3 features.
Yeah. So
and let's say, sorry?
But for that given protein.
Exactly, yeah. So it will be, so remember, what we do here is just one protein at a time. We actually cycle, loop the same way. So this table is only a table for one protein. So everything I talk about here, because different proteins will have different abundances in the runs, right? You really want to do it separately. That's kind of the point, right? You want to know how different proteins change between the runs. So we literally, behind the scenes in MSstats, there is a loop which takes protein 1, does this, protein 2, does this again, and so on.
How does it behave then if a protein has only one feature?
Oh, well, if you only have one feature, there's not much you can do. So, yeah. If you have one feature, and that's all you have, well, then you have no information if this is an outlier or if it's a real thing. And so, for this reason, in targeted experiments, you try to quantify at least 2 peptides if you can, and in DIA experiments as well.
But if you only have one feature, then you won't impute anything for the originality.
And so the solution to that is to have more replicates, because then at least across replicates you can kind of see a little bit what's going on. But if you have a systematic overlap of the peak with some other analyte, you may just have a systematic problem, right? So that would be difficult. So then the solution would be to fractionate. Yeah. But so these are, and maybe let me tell you right away that what happens if we have the protein is completely missing in one run. So then it's really difficult to do any statistics if you have no data at all, right? You cannot really impute things because everything is missing. So let's say this was condition 1, this was condition 2. So then what we actually do, we assume that this protein was completely missing from this run, and we will have log-fold change infinity and p-value 0. But because log-fold change in infinity, we know that it's qualitative and not based on the quantitative considerations. Okay, so this is the summary. So this is just a little bit more information on Tukey median polish. So that's how it works. But essentially, again, we just look at this 2-way table and we summarize by rows and by columns using medians as opposed to means. So because it is more robust. Okay, and then the last part is actually becomes quite standard statistical modeling. So if we only have 2 groups, no technical replicates, that's exactly the t-test we discussed. If it's small groups, so we can have this analysis of variance models where we can look at contributions to variation from different sources. And we can build complex comparisons such as, is the exposure to oxygen, the difference in exposure in oxygen among low invasive cell line the same as among high invasive cell lines. So we can have essentially any linear combinations of conditions. Or you can ask the question such as, is the average protein abundance at time point 3 and 4 the same as the average protein abundance of time point 1 and 2, and things like that. So you can already start asking much more complicated questions. Okay, and so that's where we can work with that. After summarization, we have model-based conclusions. And so just to highlight how this works in the presence of missing values and outliers, this is our IPRG dataset, which I introduced in the beginning. And so here we compare several approaches. So the dark red line is the MSstats. The blue rectangle like that, this is skyline, so, or many other methods. So essentially what we do, we can take the sum of all the features on the original scale and take the log. So this is very often done by software such as Skyline. So that's another option. And then these two orange, they're just linear model, essentially, analysis of variance. And this is Tukey median Polish, so looking at outliers but not at missing values. So what we can do, we can just focus on these two methods and see how they differ in performance. So if we have a situation where really no problem, right? So this was a background protein, so there is no change between condition. High abundant protein, so the light gray lines are the actual features, and the colored lines are the summarization. So you see that log of sum is above everything, which makes sense, right? Because it takes the sum of everything, right? So it has to be higher value. And essentially, there's no difference between any method. So these two have the fold change very close, large p-value, so nothing to do, right? Now, here's a situation where we have an outlier among low abundance features. By the way, this line is our threshold for limit of detection, right? And so you see that all the features were above this threshold. So here we have one feature, gray line, which is kind of outlying a little bit. But log of sum, so the green line, is driven primarily by high intensity features, right? When we take the sum on the original scale, high intensity peaks contribute more. So it was not affected by outliers in low intensity values. And the proposed approach was a little bit closer to the true fold change, but not too bad. But linear model based on essentially averages was already affected by this quite a bit more. And here's another protein, but so this time we have an outlier among high intensity peaks. And so now, so let's comparing these two conditions, condition 1 and 4, we see that the log of sum did really poorly, right? The true fold change is 1, and they record 3.5 because outlier in high intensity peaks really compromises everything. But our approach stayed much closer to the true fold change because we account for both outliers and missing values. And of course, this is kind of the real life situation when we have many features. So again, this is our limit like threshold, right? Below which we think it's censored. So we see there are many values here. If we impute them with 0, so it creates a lot of outliers. But there's also an outlier among high intensity feature. And so essentially, all the methods are somehow negatively affected. The true fold change between these two conditions is 7.5. Log of sum only sees 1.5. Linear model sees 29. Right? And so when we account for outliers in both ways, so then it really does better. And I will skip that for time, but essentially we can extend this to labeled workflows. Remember, I was saying last week that what we're doing, we're comparing deviations from the labeled references among the blue dots, right, and among the red dots. And since the deviations are larger, it points to the fact that red group is upregulated compared to the blue group. And so we can generalize this within the same kind of approaches and same data structure in the MSstats. And so it just extends our table a little bit. So I will have to skip it for time, but come to me during the break. I'll happy to tell you more about that. And of course, the experimental design. So now that we have done this, so let me just go back to the summary table. So this is where we can now look at the variance decomposition and see how much biological variance we have in our data, how much technical variance between technical replicates we have in the data, and we can learn all of these variance components. And then we can actually provide some estimates of how many replicas we would need for a follow-up experiment, which would have the same type of biological system, the same type of experimental design, and the same type of measurement technology. So we talked quite a bit about this last week. Again, if you would like to hear more, so come during the break. Or ask your friend. Remember the signatures? Okay, so very briefly, I want to make sure that Mina has enough time to do the work. Let me talk about the evaluation. So I'm really happy about the extent of evaluation that Mina and other group members did when working on this particular aspect of the workflow. So here's our IPRG dataset, which I introduced. So what we did here now, we broke all the proteins and all the pairwise comparisons by the true-fold change. So these are the background proteins, so no difference between conditions. So here we look at all the pairs of comparisons of proteins where the true-fold change is 118, 367, 433, and so on. And the columns here are, this is the method that we use, and this is the alternative summarization where we take the sum of all the features and then take the log, right? And so the blue is the specificity, so how often we do not find changes between background proteins, and green is the sensitivity, how often we find differences between the proteins when they're present. So essentially darker colors are better. And so this is just a relative performance. So you see that especially in this case, across all the true-fold changes, it is higher sensitivity without compromising the specificity. So this was the data set processed with Skyline, but we can actually do now the same thing across multiple tools and multiple data sets. So here, the IPRG data set was processed with Skyline, MaxQuant, and Progenesis. Here is the data set from the LFQ paper from Cox, and this is another spike-in data set we had, which was also shotgun. So the 3 rows are all shotgun data-dependent acquisition. So this is processed with Skyline, MaxQuant, and Progenesis, and here we also have Proteome Discover ended. And so it's hard to do uniformly well everywhere, but in many cases, you see the proposed method tends to have darker colors than other methods. So it kind of points to the fact that generally over many tools, it does better. And the same thing for DIA. So these are the 2 data sets we have, each processed with 2 tools. And you see that the left, except with some small exceptions, generally tends to be more sensitive without compromising the specificity. And so we can also look at the fold changes. So these are all the spike-in DDA data sets. The IIM also had a bunch of spike-in SRM data sets. And the x-axis is the true log fold change. The y-axis is the reported fold change. And we see that our estimates are kind of more tightly clustered than the estimates when you just use the log sum. So it also is encouraging that it essentially deals better with missing values and outliers across data processing tools. But what is most exciting for me, it's actually this. So we're very interested in maximizing the reproducibility of the type of analysis that we talk about here. And remember in the beginning, I was talking about the IPRG study and how much discrepancy there was there. And of course, a lot of this was due to like small decisions which were made in terms of like parameter selection or tool selection or some other decisions. And so what we try to do is to take different data sets. So this is 3 DDA data sets for which, all of which we know the true answer. And each of the data sets was processed with multiple tools. And so we looked at all pairwise comparisons among the true changes. And so we wanted to see how many true changes we find overall across all the tools. And so what is interesting is that with the proposed method, there's a lot more agreement between data processing tools than if we use a log sum. So the center of these Venn diagrams is what is the common conclusion made by all the data processing tools. And so with the right statistical analysis, you can actually maximize it quite a bit compared to with just simpler methods. And so this is one of the reasons why we would like to advocate for for these methods. And the same thing for DIA. So these are the two DIA data sets. So let me just do a little bit more just introduction to MSstats itself. I'm sure Mina will spend more time, but so this is just a screenshot of the actual website where we have a lot of things, including the documentation, including the code, and so on. So MSstats is also available through Skyline external tools. So we passed the 10,000 milestone, so we have more than 10,000 downloads now on the external tool alone, but many people actually access this through Bioconductor. So we have between 200 and 300 unique downloads per month. So this was from 2016, but it's the same thing for 2017. So it's in the top 20% of packages downloaded through Bioconductor. And so just a couple words about the extensions to MSstats. So what we talked about for the whole morning is really the base functionality, which focuses on detecting differences between conditions. But we actually have several group members who are interested in other topics related to this. So I just wanted to highlight two parts. So one is a characterization of assay. So just kind of to your question, right? If I want to know what is limit of blank or limit of detection, so the way it usually works, you spike, you dilute your analyte, and then compare the signal to the true concentrations using some linear model fits or nonlinear model fits. And so we actually have work related to that. And the second really important part is related to system suitability and quality control. So what we discussed here was looking at endogenous peak intensities of samples we're interested in. But when we find problems, especially severe problems, it may be kind of too late to do something about this. So what is also important is before we start collecting the samples to perform system suitability tests, where we use some standards on our measurement workflow to make sure that there is no changes in retention time, changes in peak intensities, and so on. And also interleaved with our endogenous samples, spike other standards to make sure that during the data collection we have good quality measurements. And so all of these things have in common the fact that we do it in time, right? So we profile these standards longitudinally, and ideally all the measurements remain as consistent as possible. And if we find some deviations, so this is a warning signal or a red flag that something is wrong. And so detecting these outliers on the longitudinal profile experiments of standards actually requires quite sophisticated statistical methods. And so we also have a workflow. So there is the tab here related to this type of longitudinal profiling. And so we can use it in R, but we can also use it through graphical user interface. So this is one of the few things that we have currently which can be used without our command line. So I don't have time to talk about this, but please come to me later if you are interested in that. Last but not least, so because this is the work in our group primarily, I really have to acknowledge people who did the work. I'm just talking here. So Mina has led this project from the very beginning, and so a lot of the design, it's really her contribution. Tsung-Hen, who is here, made very important contributions in the last year and a half to the design of MSstats and documentation and some new developments. Cyril is the author of the limit of detection, limit of quantification part. Eralp Dogu, who is not here, he is in charge of the MSstats QC. And of course, everybody else contributed quite a bit as well. So I want to make sure to acknowledge everybody who is here. Okay, thanks so much. So I will be back tomorrow for more things, but I will hang out here a little bit if you have questions. And now it's Mina's turn.
Everyone has a flash drive and material. Okay. So please copy. because I tried to put some HTML file or some script in GitHub. However, some data set is really big, so there are some limitation I can put over there. So the old materials in the flash drive. Before we start, and then everyone has a sticky note like what we practiced the last time. The pink and blue one. Could you circulate it? Anybody has like some sticky note? Everyone has it? No. Oh, okay. I think it's a front. Yeah, this front side. Yeah. So let's go to the everyone can access this GitHub one. So now we have a program 5 for step for MS, and here we go. And then there's an Etherpad link. So people who attend the last module program 3 probably already familiar with this one. I opened another note for these sections. So if you click this, okay. Yeah. Easy way is go to the GitHub and here search May Institute. Or I will send the link just after this section during the lunchtime. So here's the Etherpad. So here I just make a day 1. So if you have any questions about today's material, or do you want some very specific topic, do you want to talk about this, please write it here, and then I will try to find some way we can cover tomorrow. So here it is. Then let's open the folder, what I shared. So if you open the folder for material, this 3 is for today's one. The section 1 is for this section, and section 2 and 3 is for this afternoon. There are several folders for each data set. So we are going to work with the same data set, ABRF1, but we process by different spectral tools. So here, for example, this one is output from the skyline, the same data set. And then this one is the output from the max quant. And this one is, from the progenesis. And this one, data SN is from the spectrum, but not for the same data. So this one for the DIA one. If we have a time allowed, I will show you. However, this is for DIA data set, but probably I will talk about this one probably tomorrow morning. And just in case, here backup folder, I just put all the output, what I expected from today's one, just in case if you miss it, just look at this one.
Remind yourself about the stickers. So if you have not been here, so there's a pile of stickers here. Somebody needs them. So the idea is that if you have a question, put a red sticker on the back of your laptop. If you feel like it's going too slowly, you're better than you want to move on, put a blue sticker on your laptop. And so we will be walking. So Cyril, could you please wave your hand again, and Sung and myself will be walking around and watching out for the red stickers, or just hand waves.
Can you read? If you just there's only one folder in the flash drive. Just copy that one. Is it possible to read? Okay. So please open the RStudio. So the goal for today's hands-on is to master MSstat. Okay, the master MSstat. Could you raise your hand if you have any experience to use MSstat before? Okay, so very few. Okay. As we mentioned, we have several channel to use the MSstat, but this one now we have a lot of the functionality and then try to expand as much as we can to across all the spectral tools. So today what I'm gonna do is with the ABRF1, there are several input for different spectral tools, and then we're gonna repeat the same workflow with a different data set, a different spectral tool, and then want to compare. So just to repeat it. However, you can see some difference one. And this is, we are gonna use the DDA data set because it's helpful to actually, we can see what is our contribution for the protein quantification. However, it is also it's okay for SRM and DIA cases. So before we start to use the MSstat, I know everyone should be installed the MSstat1, but let's try to, I actually updated something for MSstat. Let's try to do this. So go to the RStudio, click Tool, click Install Package. If everyone have a problem, please put your pink sticky one, and then people, the TAs will help you. Install package. The here is really small, but if you click here, one is CRAN and one is the package archive files. So click package archive files. Then it shows where is the package. So under the folder, what you copy, here's MSstat 3.8.1 tar.gz files. Click and OK, and here install. So the MSstat -3.8.1 for tar.gz. If everyone is succeeds, please put the green note over there.
Make sure you don't have MSstats loaded. Make sure you restart your RStudio before you try and install it.
Okay, so at the only moment we can working without the MSstat. So let's go a little bit, and the installation issue let's handle during the lunchtime. Okay, so just to remind, this is the data structures. This is the DDA one, and it includes a quantified peak intensity, and we have a 6 protein spiking, and there are 4 different conditions, and each one we have a 3 technical replicate. So, for example, this specific protein ID, they have this amount with spiking. So, means for this specific proteins, condition 1 should have more than the other conditions, and so on. And there are background proteins, more than 2,000 proteins there. This is just background. It should be equal amount across all the conditions. Okay? So, I will show you. First, I will open the new file, iScript. I will make a script for analysis for Skyline output. So first, we need to load MSstat. We need to call MSstat. Okay. Then, if you want to know what kind of functionality and option we have, question mark MSstats. And here it shows version and the date and so on. Okay. Then we need to first check what kind of input we need for MSstat one. Okay. There are several small data set in the MSstat. One of the data set is I can call SRM row data. It will show first 6 row only. Just double check what kind of input format we needed. Here it is. This is the required columns for MSStat. We need protein names. We need a peptide sequence, precursor charge, fragment ion and product charge, and isotope level type. This is SRM data set. So that's why we have a heavy and light type. If you have a DDA, you will have only light one. And we also need annotation for conditions and biological replicate and MS run, and then quantify the intensity value. So 10 columns we need it. Okay. Then with this data set, this is the whole kind of the summary of what MSStat doing. So first, you did some sample prep and then experiment, and then run through the mass spec, and then you have a raw data. Then there are several spectral processing tools, Skyline, MaxQuant, Progenesis, and before you need the identification too. So you can do peptide identification and quantification from the other tools. And after you got the quantified peak data set, peak intensity, it is the point you can use the MSStat. So I just make this box. This box is only for the MSStat one. First, read the data output from any processing tools, and then we are going to reformat it for the MSStat required format. MSStat have 5 different functionality to convert to MSStat required form: Skyline, MaxQuant, Progenesis, and Proteome Discoverer, and then SpectroNet. So for 5 processing tool, you can easily change to MSStat input format. If you have in-house tool, actually you can write some script or function to automatically generate the MSStat one. So for this section, we're gonna practice this part, and then next section we are gonna practice another step. Okay. I will practice with the Skyline output. Okay, so let's go to the R Studio and let's find the place what I saved. So here is the folder what I have. It's really tiny, but this is the folder what you copied, and then I make this is the working directory. So click more and set working directory. Anybody knows how to change this font? I changed here. Comment. Oh, shoot. Okay. Then I will reduce this part. Yes. Okay. Yes, I will just want to show the what input look like, so you don't need to worry about what the data look like. Just focus on the what kind of the column names we have. This is also one of the data SRM, but data structure itself is same, just protein name and quantify the peak, but a little bit different annotation. So under the, if you click the data skyline, ABRF 2015 skyline report is from the skyline. So if you are familiar with the skyline, in the skyline, you can choose the report format, and they already have an MSstat report. So if you want to extract that one, just click, and then you can automatically generate this MSstat the format one. But this is the what we generated. Then let's read this data. So I will say row skyline, read CSV. Just one tricky part, quotation mark. Our directory is here, but our data set in this folder. So you need to make, this is under data skyline, and this is the name, the ABRF 2015 skyline report CSV. And mine is reading the data set. So I have a cursor here, then I can see our row skyline file. So head row skyline will show how the data look like. Okay, so skyline, if skyline output, here is what we have. Skyline output, they have a protein name. This is one of the what we want. Peptide sequence is also what we want. Peptide modified sequence, basically we are gonna use this one for the peptide sequence, and so on. But you can see the condition information, they have NA. They don't have condition informations. Here, biological replicate also, they don't have this information at all, which means we need to put this information in. Instead of the run, they call this as a file name, the raw file name. And instead of the intensity, the column name, they use the area. And they also report to several extra columns. Here's a standard type. If you go to the skyline, you can choose which peptide you want to use a normalization and so on. And then they also have some column for truncated. So if the peak, for example, if peak should be like this way, and then they want to calculate the support area for peak intensity. However, based on the retention time cutoff, if they have only this shape of the peak, they think this is the truncated, and the intensity value is not correct. So they have a true false value for this peak intensity. And then this is annotation Q values. This is especially for DIA data set. If you have another identification score one, they also report this one. So in these cases, we also use this information to how to handle the intensity one. So this is basically how the other skyline output look like. Then let's try to dig a little bit what they look like. So this is the column name. However, whenever I read all the data set, I always do some preliminary check. For example, first I want to check how many protein ID they have. Unique length, unique, row, skyline, protein, names. Here you cannot see this. Just you look at this part. They show all the full code, what I type it here. There are 3,097 proteins they have. And also, for example, skyline cases, they report the isotopic peak. So how I can check it is they report in the fragment ion column. For fragment ion column, they report the 3 different isotopic peaks. Okay, and also let's check how they report for truncated one, skyline and truncated column. They have a true and false values. If truncated is true, means we don't want to use that specific intensity, means we somehow need to filter in one. So if you want to count how many truncated peaks we have, you can just make a table. The X tab is make a table based on truncated column from row, skyline, X tabs. It shows there are 829 truncated peaks in this data set. Yes?
When would you get truncated peaks? When do those, I see what you mean by what a truncated peak is, but when do they occur?
So the skyline automatically generate this column. So they already have some report to format. for everything. They just make an automatically truncated column.
I think the question is how it comes about, right, in the first place. Imagine you have a target experiment and you schedule your attention time window and you misschedule this. And so the peak is moving outside of the time window.
Okay. So as we briefly see in Skyline output, they don't have information about the condition and biological replicate. But we need the condition information to know what kind of condition we want to compare, right? So pretty much all the output, we need annotation table. This is not generated by the spectra tools. This is based on your experiment. So you have to generate this annotation table one. So if you go back to our folder, data Skyline, there's another CSV file, Skyline and annotation one. Okay, the Skyline report, Skyline generated. A Skyline annotation, you have to generate it. So let's open this. So we need these 3 columns. So they already know this specific intensity came from which specific MS raw files, but they don't know this is what kind of information they have. So this run column should be exactly same as the unique raw file name in your Skyline output. But for corresponding each MS run, you have to say, okay, this came from which condition, and this came from which biological replicate. Yes.
Sorry, so you have to make this table yourself by hand?
Yes.
Okay.
Yes. So easy way is you can extract this information from raw file, but this part basically you have to type it. Yeah. Yeah. Okay. So here what I made it, but I will talk about the 2 common mistakes about this annotation one. This is the most common question that we can get from Google group site. So now we have a 12 run. So absolutely we have a 12 rows we have. Actually, commonly raw file name is really long. And then very easily they have a typo. And then very tiny changes. For example, this and this. Can you recognize what is difference? I will make this one is larger. This versus this. Yes, one is under dash and then like this one, right? When we make this one, we just copy everything and then just change A, B, C, D. However, this mistake actually happened. If it's not same, they cannot recognize this actual specific run came from which one. So you need to double check. Here, this one also have some typos, right? So that is one of the common the mistake. Number 1 important. And then second one is how you can annotate the biological replicate.
Can I take a second and have the sticker back up? Because I feel like some people are a little bit working on some issues, just to make sure. Everybody will see that blue or red sticker just to know.
Yes, yes, yes. If we don't know this issue later, really at the end, we can find there's something wrong, and then error message will become. And then this one is I really want to make, this is really important. So based on this condition column, and biological replicate column and run column, MSstat recognized what kind of experiment design you have. We have 3 experiment design we can cover. One we call group comparison, means we want to compare 2 groups, disease versus healthy group. Okay. Then, for example, let's make it easy. Cancer versus a healthy group. We take 10 samples from cancer, 10 samples from healthy subject, right? Means these 10 subjects should be completely different, right? One person can have cancer or I don't have cancer, right? It should be different. Which means when we annotate condition and biological replicate, this should be really subject ID, unique subject ID. Okay, so if this is A sample and this is B sample and C sample, these 3 should be completely different ID from here. Okay, it should be D, E, and F. We call this is group comparison. Okay, this one is not same as this, right? Then, if very common question is people just put this one is A, B, C. People say, okay, this is a replicate from this condition, and this is a replicate from this condition. However, in statistical, it's different, right? They say this is a biological replicate, same biological replicate, have a different cancer means they think these 2 samples from same subject, however, probably from different tissues. Okay, this is we call the pair design. From one person's, they have several different measurements, and then we can. This is actually from the same biological. Is it okay so far? So previous one, okay, I will say here. This we call group comparison. And we call this is a pair design. Okay. And another last one is time course design. Okay, I'm the person, and then I have disease, and then I got some treatment, and then they just take my blood 1 month later, and 3 months later, and then 10 months later. Means I'm the same person, but they have a different samples, right? We call this as time courses. In their cases, it should be like this. They have to recognize the same replicate, however, they have a different conditions. Depending on how you can annotate this versus this, actually we have a different modeling used for our hypothesis testing. Okay, so this is the most common one. Yes. Yes. So this one is important to make a formatting, just to make a formatting. So we want to make this information and then skyline output, because the skyline output, they don't have the biological replicate and they don't have a condition information. For each run, we want to say, okay, this specific run for condition 1 or biological replicate 1. If the run information is not matching like this, they completely cannot assign this sample came from which condition or which biological replicate. So for example, now we found here the 2 run is kind of a little bit different, right? If you make this one, it's like this, they lost this information. And now we use only 11 that run information. instead of the whole 12 line. Yes, yes. So annotation file should be exactly same as the raw file name in the output. Okay. So that is the common mistake one. Then after this, after you ready for skyline output and ready for annotation one, we can use the skyline to MSstat format function. So I will just, before I try to run, I will just explain a little bit. So here is the what skyline doing. You know, skyline generates some output, but internally they already have some filtering strategy. So if they have a duplicate row, means for their specific features and for specific run, we expect they have only one values. However, quite commonly processing to generate the several the intensity value. Then we need to decide, so if they have a multiple intensity value, which one we have to use it. So Skyline already have a filter out, and then they also removed the decoyed one, and then they also removed some proteins which have only one peptide per protein. This is what Skyline do. And then it's come back to the MSstat. At the first stage, when you transform our format, we just rename the column name, just exactly what we need. And then we replace intensity for truncated row to NA. We think this is just a missing value. We cannot trust this value anymore. And then among the 3 isotopic peak per peptide and charge, we sum of them, and then we are going to use that one. So this is basically what inside this function what we are doing. Okay. So it's quite similar across the different spectra tool. However, there are somehow a little bit changes, and then I try to make a default option, which is best performance. So best performance one after we testing quite a lot of the data set. Okay. Then if you go back, what we can do is, okay, then I will make a skyline output to MSstat input. So input skyline, if you just put the skyline, they will automatically show the function name. And then the data set what we read, row skyline, and annotation. Oh, we forgot to read. Okay, so let's go back to them. We need to read the annotation file first. So skyline is also in the same folder. Read CSV dot data skyline, and exactly same as this one. ABRF so this one. Then I can check on a skyline. So they have run and condition biological replicate ID. Ever read the annotation files? Then here is the transform one. Okay, annotation. Okay, I lost annote skyline. import, yes. Import this one. It should be, no, it should be original. Yeah, old one is also should work. Yeah. So ABRF 2015 Skyline and annotation.csv file. This one, yeah. Yes, you don't need to be warning message, means they just replace this one to NA. So this is another error message. This just give you the warning about they just replace to the NA, so you don't need to worry about this one. Mm-hmm. I think so. Yeah, but this is also same option. Probably I just changed it for true, false, or for true, or some. Yeah. If somebody succeeded so far, if you want check, you can check head, input that skyline. We show updated one. So if you scroll here, they have a protein name, peptide sequence, L, and now they have a condition information here. Now they have a biological replication information here. And then instead of file name, they have a run and intensity values. Okay? As a head of input.
Let's have a sticker update again. So how are we doing with
So people who succeed, let's check how many unique protein they have, how many zero values they have, how many NA values they have. So three things. If somebody succeeds to get the input, this one, unique number of the proteins and zero and NA.
Yeah. Oh. So whenever you're in the insight quotes, and in general, RCA will just tab complete. So if you hit tab, it will show you all the options. Then you can use arrows to select the options. It's all right. Once you do quotes on it, okay, start reading the directory. So you can sort of navigate through, right? So we're doing skyline, hit tab again, now it's the files there. That completes your friend.
Maybe I studied this one for DDA. So searching result, but as I remember, they use the common and an MG, GF, and OMSA, something like this. But more detail is So if people succeed this one, I said the three things check. First, let's check how many unique protein ID they have. So length, unique, input, skyline, and protein names. So now we lost 70 proteins because we removed some protein have only one peptide ion, one. And let's check how many NA's value they have. Some is NA, input, skyline, and intensity values. They have 233 NA values in the intensity. Okay. And let's check how many zero value they have. Some, it should be first, it should be not NA. And this one. They have more than 2,000 zero value they have. Okay. So skyline output, they have a zero value and NA value. So we are gonna practice for max quant and progenesis. They report differently. So let's see how it goes. So this is the skyline input to ready to use the first function in MSstat. Then let's save this one. We are gonna keep using this one. So let's save input skyline file please place the blue one if you succeed to save the input one. Save as
.rda.
Yeah, .rda. Okay. I will save this R script to keep the R script for whole the skyline analysis. So I will save this. Click save this script. I will say R script for skyline. Okay. Then I will open the new script for MaxQuant. How many people have you used MaxQuant before? Okay, so MaxQuant, if you process everything under, I guess, one of the folder output or something, they generate the several output, like evidence file and protein group file, the peptide group file, somehow they summarize the peptide level or protein level and so on. However, we are gonna use the original one without any summarization, only really at the full feature level one. So first, for MaxQuant, we need three files. One is for evidence file. So let's read it. I will call this is the AVI, but this is a TXT file. So rate table. And okay, if you see our folder here under the data max quant, we have evidence file and group, a protein group file, and also annotation file. So we will use all three. So evidence, we will read this specific folder, data max quant. Evidence.txt. Separate by TT and header true here. Okay. So if you check how the evidence file look like, it's really big data and then complicated. So we need to extract what we require. So if you want to check the evidence file, column names, AVI, it showed all the column names in this specific TXT file. So you don't need to worry about it. We're gonna automatically extract it. And then we also need the protein group information. So I will say protein group, and this is also same thing, read table, data under the max quant, and the protein groups TXT file, separate by T, and header true. Okay. People succeed, please try to open this annotation file under the max quant, and then please tell me what is the difference than what we used for Skyline. And the column name, how about the column name? Yeah. What they say? Raw file. So here, instead of the run, we have to make this column name is raw files. Raw file. And then you also recognize that here they don't have .raw, right? Yeah. So this is how the just max quant recognize this one, and then I also need to this raw file information with this annotation one. So that's why we have this one. And then isotope labeling type is max quant also working for SciLec or something else. They have also different labeling strategy. So that's why I said we also need this isotope labeling type one. So this is a little bit different than what the Skyline did, right? And let's read this annotation file. Same thing. I say annote maxcon read CSV under the data maxcon folder ABRF CSV then we are ready to convert to maxcon 1, and then this is what we are gonna do it inside of the maxcon converter function. They also have several additional information for maxcon. So here is if you have a contaminant one or like some reverse sequence one, we are gonna remove it and so on. So and if they have a multiple measurement because of some identification score or some different or slightly different M over G or something like this, we use the maximum value because we feel this is better than highest value based on our other testing. So this is the whole procedure what the maxcon converter will doing. Then now you're ready to use the maxcon converter function. So let's make an input for maxcon. Input maxcon. Here, if you type max, it will just show you. And then we need to type evidence file is evi. And annotation is what we read, annote maxcon. And then protein groups is what I made a protein group. Basically, we need to enter this three information. Then click run, and then it will show what they are doing. The first, the contamination and reverse sequence is removed. The peptide including M sequence are also removed, and so on. It shows the whole procedures. And also, especially, they also remove the peptide charge stage, which have a very few measurements, just 1 or 2. Because this is also problematic for when you apply the statistical model for further analysis. So now, in my page is done. Then I can check how it look like for input maxcon. So head input maxcon. Oh, I see. Now input maxcon, they have a protein name, peptide sequence, and so on, and then what we needed. Okay. Then this one is ready to use. So now it's 1:30, so we are gonna come back at it's now 12:30. We are gonna come back at 1:30 to start with the progenesis output one. Then at that moment we are gonna start actually how to make a summarize and then how to make a testing results. Yes, have a good lunch and please let me know. I will stay here during the lunch time. So if you have a question, just let me know.